it's possible to use this kind of statistics, hypothesis testing, to compare different samples, means from different samples. And in fact, in this case, here's an example I've used for some years now. I have final exam grades from two different Math 160 courses. In the winter of 2002, the class averaged 77.2 on the final exam versus 81.0 in the summer of 2001. So summer did better in this sample. The standard deviations were similar, 13 point something. And sample size, there were 11 people in the winter class, there were 14 in the summer class that year. So the hypothesis test of this one will be comparing the difference between two means. And now there is a difference between the means of these samples, of course. It's about, what would that be, about 3.8 points between summer and winter. So what exactly are we trying to compare here? Well, here's how I would structure the hypothesis test. The null hypothesis, we would assume that there's no difference between winter and spring. I'm sorry, winter and summer. And so we're trying to see, is this enough evidence from these samples, is this enough evidence to conclude that winter classes score less than summer classes? All right, now, you could certainly have some problems with those assumptions, because is it fair to let one class represent a sample from all winter classes, or a sample from sample class represents a sample from all summer classes? All right, but if we made that assumption, then we're comparing winter classes versus summer classes. And the null hypothesis would be that there is no difference. Now, no difference, we can say it this way: the summer scores would be the same as the winter scores. So I wrote it symbolically as null hypothesis is mu subscript summer, S, is the same as the mean for the winters, mu W. We could also say that, alternatively, that mu S minus mu W is 0. In other words, the difference between the two means, population means, would be 0. Well, the data, of course, was different. If these numbers were the same, we wouldn't be interested in doing a hypothesis test. But they are different. And to me, it's a close call. Is this difference significant enough to say that summer classes do better than winter classes in Math 160 on the final exam? The difference is, what, about 3.8 points. Is that enough? They are small samples, so I don't know. But that's what we're testing. So the alternative hypothesis from this data, you would have to say, well, the mean scores from summers are going to be greater than the mean scores from winter, because this number is larger than that. So we're looking at possibly this result, but what we want to know is this enough evidence to conclude that's really true, or was that due to randomness, random fluctuation, when in fact there is no difference. All right, well, testing the difference between two means, and you'll find the formulas on page 295 of your book. And this is one of the more complicated calculations we do during the course. And it's really two-part, in a sense. First, we have to calculate the pooled estimate for the standard deviation. All right, so what does that mean? In order to use the formula in the middle of page 295, we need to first compute the one near the bottom of page 295. So they have S squared is equal to, and I'll write in the formula here, if I can fit it, n1 minus 1 s1 squared plus n2 minus 1 s2 squared divided by n1 plus n2 minus 2. So I hope that's Hope that's readable on your screen there, but it's right from the textbook on the bottom of page 295, so you can get it from there. This calculation is a type of average of these two standard deviations, but in order to get it to work right mathematically in all the theorems that underlie the statistics, we need to calculate a single standard deviation from these two standard deviations, and it involves not just these standard deviations but also sample sizes. So you might think of it as a sort of a weighted average. It's not a true weighted average. I'm not sure what you would call it. To me it's kind of a weighted geometric average, but I'm not sure that's quite accurate to say that. Anyway, suffice to say, we have to do this calculation first to figure out what's some textbooks will call the pooled estimate for the standard deviation, S. So I'll plug numbers in, and it's going to be hard to fit all these calculations on the board, so I'll have to erase some of this stuff. But S squared would be, well, one sample is N1 minus 1, and so let's just, and you notice I used more descriptive subscripts than 1 and 2. I used W and S for winter and summer. So if I use this one as my N1, this would be 11 minus 1 is 10. So I have 10 times its standard deviation, 13.3 squared, plus N2 minus 1, so that would be 14 minus 1, 13, times 13.9 squared. Again, I hope this is fitting on your screen, but it's 10 times 13.3 squared plus 13 times 13.9 squared. And the denominator will be 11 plus 14 minus 2. Well, let's see what that works out to be. Now I'm going to calculate my numerator. 10 times 13.3 squared plus 13 times 13.9 squared. And I get 4,280.63. Denominator would be 11 plus 14 minus 2. It looks like it's going to be 23. So S squared is 4280.63 divided by 23. I went ahead and divided. I got 186.11. But now I'm going to take the square root because I really want to know what S is. So this calculation here, we need to take its square root. And I got 13.64. So S is 13.64. Now notice S is between these two standard deviations. And it's pretty close to the middle. It's a little more weighted toward this number because it's a larger sample. But it's close. And so that's going to be the standard deviation we use for the next calculation to calculate the t-score. So a little complicated, but I'm going to erase, well, I'm going to erase this part here, so, and then we'll calculate the t-score. Now, they have another little calculation here on page 295, the degrees of freedom. And the degrees of freedom is the denominator of the calculation I just did. So the degrees of freedom we'll use is N1 plus N2 minus 2, which worked out again to 23. So the degrees of freedom, I know that may be a bit of a mystery still to you, but the degrees of freedom are, that little calculation makes it possible to use the student's t-distribution chart for many types of statistics. So in this case, you might think of it this way: we have two variables, we have 25 total samples in two variables. So 25 total samples, we subtract 2 because there are two variables, and we get 23. So that's pretty much how that works.